All right, everyone. So, welcome to the second of the spring Tech Exchange seminar series. And we have two speakers today, and I'll let them introduce themselves before they start. But the objective of this is to sort of make folks across the university aware of the various things that are going on. Typically, people tend to are busy with their own lives, and like there are lots of activities within departments, but across departments and across the university, people tend not to be familiar with what is happening. And our objective here is that if people do listen to all of this, and we will have the recordings available, we'll also try to publicize it even more. But hopefully that will foster more collaborations between faculty across schools, across departments, and lead to more beneficial research. So my name is Ranga Settler. I'm the Associate Director of the Institute for AI and Data Science. And I'm also the Managing Director of this National AI Institute for Exceptional Education. And our first speaker today is Roshan Ayyalasomayajula from Computer Science, and I'll have Roshan take it away.
Okay, that's the one. Okay. How do I control the slides?
Yeah.
Awesome. Can you guys hear me now? All right. So, hi, I'm Roshan. I'm an assistant professor in the Department of Computer Science, and this is my second year now, right? So, and my work mostly is in wireless systems. I work towards developing, or as some of us say, remove wires wherever I see one, even this one if possible. I try to make things more robust and deployable for real world settings. And today I'll be talking about how ML or AI algorithms can be deployed or can be used for most of the mobile systems and robotic algorithms, and even how I'm using them for my own lab, right? So, my work spans multiple domains since I work with wireless sensors. I try to imbibe them anywhere I can go. Um, so we have developed robots which can just use Wi-Fi plus IMU to navigate around. We are developing wireless localization app that I hope one day everyone in the UB can be able to use to navigate around. And we also are trying to do something more interesting where you can see this is quite a huge robot, cannot go into all different spaces. So we're trying to miniaturize it, make it tiny enough that it can crawl anywhere you want it to by just using minimalistic sensors, and Wi-Fi or wireless sensors being one of them. Right. So ML or AFI robotics, and how or where is it used, right? Before I go there, I would like to talk about something called SLAM, where it basically means simultaneous localization and mapping. So given any task, let's say for the robot here to traverse in this unknown environment while watering these pots, could be a task, right? For this to happen, the robot should know where it is in a global sense. And it also should have a sense for the global perspective, right? Basically, it should know the environment itself. So those are the two different tasks first, or underlying dependencies it has: localization and mapping, right? So how does it do that? It does with its multiple myriads of sensors. If you just have, let's say, a tracking sensor, a click sensor, or a integrating sensor like IMU, you can just get the position of the robot. But it drifts over time, and you can't map the environment per se. So the other thing is to add visualization sensors, which are cameras or LiDARs, and they sense the environment. And like people, as we see the environment go behind us, we estimate that we are going forward in the environment, right? So the robot does the same. It tracks or it maps the environment, and as it tracks how the environment is moving, it corrects for its own pose updates, right? So that's the back and forth that happens between localization and mapping. And there's a lot of different algorithms that we can do here. The first and foremost, once we start mapping, for the robot to understand that two different pixels are different, you need to do something called feature identification or object detection. And we all know how computer vision and ML models are useful there, right? So that's one of the pipelines that has been used for the environments in general, or for these robotic deployments in general, right? But then, not all environments are feature rich, right? So this environment, for example, has some features, right? It has two different pots. So as the robot moves forward, the flower pot keeps changing from the left to right, and there's a corridor in between, and so on and so forth, right? But then, let's say we don't have those potted plants anymore, right? It's just a monotonous corridor. So as the robot moves forward, it keeps seeing the same environment over and over. The number of features does not change because it's just a monotonous environment. So unlike us, the robot has limited understanding of this environment, and much so if it's actually darker, right? And in this environment, let's say we were able to actually, and this is where we actually make use of multimodal sensing, right? Limiting ourselves to one singular mode of either visual or visual sensing or LiDAR sensing is limiting in itself, right? On the other hand, it would be much better if you can actually do it with multiple different modes of environment sensing, acoustics or wireless sensors, my favorite, I guess, there. So these are the different forms of sensing that I usually like to talk about. Each of them has their own advantages and disadvantages. Camera, on the one hand, has really high resolution, decently long range, but it is easily blocked by obstacles or is dependent on the visibility of the environment itself, right? And on the other hand, wireless sensors have a relatively poorer resolution compared to a camera-based sensor. But they have long range. You have cellular that has few kilometers of range, and Wi-Fi up to 50 meters or 20 meters, right? And then these are actually robust to obstacles. Because they transmit at lower frequencies, they can actually pass through many of the daily obstacles like the walls and everything. And that's the reason why you get a cellular reception in a building and not a GPS signal, or you can't see the building, right? So, going back to this environment, so now in this environment, we want to add a sensor that actually gives us more diverse landmarks in this monotonous or darker environments. And the way to do that, let's say I tell you that actually there is a sensor that gives these unique images at different locations. And that actual sensor is your day-to-day Wi-Fi that you use for communication, right? So Wi-Fi sensor that you actually just use for connecting, let's say, let's say the robot just wants to connect with its peers and it is using that Wi-Fi for just connectivity, right? We can actually take that same sensor, take that same Wi-Fi transmitter or transceiver and use that as a sensor that can aid now in our SLAM or robotic motion. And I think, skip the details on how you get this exact profile. There is a bunch of math in how you do fast Fourier transforms on the received signal, not the data, but the signal itself. Irrespective of the encryption, you can still do this, right? So you can get the bearing on where the access point is deployed and how far the access point is as well in some contexts. So using that, you can actually get this profile, which actually is nothing much but saying how far the signal has traveled from and from which angle, right? So it basically gives you the origin or the source of the transmission of the for a signal that you're receiving, right? So that actually ties in very well with the mathematical model for localization itself, and which then in turn helps us in actually navigating the robot or constraining the robot's SLAM graph. And I'll skip this for now. And we have actually shown that given that you have just Wi-Fi in turn with your IMU, Wi-Fi and IMU together, you can actually correct for most of your drifts in the environment without needing even any visual sensor on board, right? And so the blue line you can see is the ground truth estimated from a LiDAR-based sensing cartographer, which has very accurate SLAM performance, very high SLAM performance. And in the orange on the right, or on my left, is what you see from the Wi-Fi-based SLAM, right? And on the right here is just the Wi-Fi, the orange on the left here is just the pure IMU-based dead reckoning, right? And you can see how it corrects for all the integral errors by just using already existing Wi-Fi sensors on board, right? And then we ventured into something something of what we call multimodal sensing. So multimodal, like I said, so far we have just seen Wi-Fi plus IMU, so that's just one sensor more or less. IMU is more required for any form of motion. And so next we wanted to do actually include these Wi-Fi sensors into existing camera or LiDAR-based sensing, right? And how do we do that is through so the one simple thing we have observed is these camera-based sensors need to actually understand what when they see the same location, right? Or what we call them as loop closures. So let's say the robot has moved around in this environment and has seen the same potted plant at two different locations, right? While there are two different locations in its own local perspective, they're actually the same location in the global perspective, right? So the robot has to always close this gap or close this loop. And not just close, it also has to always search for this loop, right? Every instance, it has to see if it is doing some loop, if it has encountered a loop or not. And that basically means infinitely long memory. Like it has to store every frame because it doesn't know when the loop is getting closed. And it also has to keep comparing with the past, the current frame with the past frames to see if it is a loop, right? And both of these in tandem actually start making the system more and more compute and memory inefficient because you need to store all the frames for all of the eternity as you go along in the time. Your memory is going to increase linearly, and then your compute also keeps increasing because you're comparing with more and more images every time step, right? And so loop closures are a big hurdle in terms of deploying them on a mobile robot, which is, let's say, a tiny robot, right? You need very high compute, like a Jetson TX Nano or something. If you wanted to run this on a Raspberry Pi, it would be a bit more harder. So the idea is, because the robot has what we call as ego sensors, where basically the robot itself is trying to sense the environment from its own perspective, like the cameras, LiDARs, IMU. It is limited because it always has to estimate where its own location is with respect to the moving environment. On the other hand, if you had some landmarks, if you've seen these Argo markers or QR code-like looking markers, they are visual landmarks which help you tell where specific exact location is in the environment, which basically is a form of environmental feedback, right? And that's for the cameras. And on the other hand, we can for the world of Wi-Fi, these landmarks are already existing. The routers I was talking about earlier already exist in the environment. They're unique. They have a unique ID, and they're at unique locations, right? So as long as we can map those routers accurately and then map yourself accurately, you will be able to get remove all the loop closure requirements and make the system entirely efficient, which we actually show and demonstrate that Wi-Fi actually makes SLAM efficient. Adding just a Wi-Fi sensor on board makes your SLAM that much more efficient because you're getting feedback from the environment. So then a question here of what is ML here? That's a very big ramp up for anything on what parts of ML are we using here, right? So one interesting thing that we have started to observe is, like I said, I try to remove other sensors and put in Wi-Fi as much as I can, or wireless sensor as much as I can. The question we had is, can we just use Wi-Fi or radar sensors to map any given environment, right? So let's say we have this entire space. We have shown in P2 SLAM that using Wi-Fi and IMU, I can just navigate indoors, right? We have then imbibed that into a camera SLAM, right? And we have seen that it makes it efficient. But can we even remove the camera completely out of the picture and just use, let's say, a radar? The major purpose of this could be privacy, where no one wants to take for the robot to take their pictures, and also some form of seeing through obstacles, right? So a robot going through, let's say, this glass pane would just see that there's a glass pane here. But for a radar, it will actually see that there are some desks behind as well, right? So that's the advantage of having wireless sensing, right? So the biggest problem, though, there is, like I said early on, wireless sensors have really, really poor resolution compared to camera sensors, right? In a camera, a pixel might come to a resolution of even a millimeter, right? But in a radar, even a high-end radar with 1 gigahertz of bandwidth can give you a resolution of up to 4 centimeters or 3 centimeters, right? It's not sufficiently high enough. So how do we go from there to doing something more interesting? That's where there have been recent developments on using diffusion models, or specifically the NERF models for RF, where you map the different signal strength measurements on. So basically, the problem with trying to simulate RF measurements in the simulator world, or try to in-paint Wi-Fi signals everywhere in the environment, is that the Wi-Fi signals don't just do specular reflection, but they also do diffractions and so much more because of their wavelengths. And so you have to solve these high fidelity models of Maxwell equations at every location, which makes it that much more hard for even a supercomputer to do. And NERFs, on the other hand, actually simulate or extend these wireless signal models throughout the environment much more simply and give us a very good map on how wireless signals diffuse in that environment, right? And so using this, we know that using a camera sensor for this environment, we can get an RGBD cloud and do some object detection on obstacle detection in that world. And in this world, if we can actually get accurate diffusion patterns of the wireless signal, we should actually be able to map something what we call as electrical permittivity and magnetic reflection, or there's the reflection coefficient of these environments, which would help us simulate the environment for RF or the radio frequencies, right? And so there are two different perspectives here. One is trying to use diffusion models or NERF models for RF, and then extending or approximating your Maxwell's equations to actually go back and estimate the material properties, the electrical material properties, the relative permittivity, reflection coefficient of these all obstacles, so that you can actually map the environment for the wireless signals, right? So that's the I guess the ML AI perspective that I try to use. So basically, now that you have these accurate ML-based wireless models, you can actually simulate various transmission patterns and diffusion patterns, and give feedback to your real world environment where you can actually now develop digital twins for these RF models. There are digital twins for every other, mostly every other sensor modality, at least camera and LiDAR. This would in turn actually give us a perspective on the diffusion, or rather or this will help us develop digital twins for your RF models. I see the time. I have to also run for a class. So I'll skip the second half of this completely, and I'll skip towards questions. But the high-level idea for the second half is using something of the form of federated learning for yeah. Or if I can go back one step, or is it at the form? Okay, right, there's an well, there you go. So doing something on the form of federated learning for estimating accurate indoor location, and we are in the process of actually developing or building this app through ELR CSC 302 303. If you're not familiar with it, it's a very wonderful team. We get to develop these apps. We are deploying this on the local servers within UB itself. So we are trying to see if we can actually get some data and also then use that data for machine learning, and then locate everyone indoors, or rather help you navigate indoors. So far, we were able to successfully map Davis first floor and third floor, but we're trying to expand every semester. Hope.
Contribute data for you?
After the semester, we should be able to open this up to public. I think we are still in development phase, testing it out. I think the students are testing the data collection rather this week. So once we have a stable version of this app, we will open source it and put it forward for everyone to use. So this would be the first step of any MLAI model, data collection. So help us out. Cool. Thanks a lot, everyone. Sorry for running through a lot of jargon. I know it's a bit too much, but let me know if you have any questions. Yes.
Yeah.
You did mention diffusion models. So could you just like talk very briefly about what kind of are these conditioned models? Like just.
So the way I look at it, I think my experience with diffusion models is a bit limited. I've read it once long ago. The idea is following: any wireless signal is riddled with elder wide Gaussian noise. So the farther the transmitter is, the weaker the signal you get, because the noise is higher than the signal itself, right? And the way I understand it, most of the diffusion models have been used, or at least when I was starting to read it, for denoising images. The idea here is, what if we can denoise the wireless signals itself? That way you can actually extend the range and get more accurate readings for even longer ranges of measurements. And the transmitter, you don't need to take the transmitter to different locations. It can just stay farther enough so that you can actually map big enough environment. For the conditioned models of it, I'm not completely sure. Okay. Anything else? All right. Cool. Thanks a lot, everyone. Yes. I'll run. Please feel free to email me anything at roshana@buffalo. I'm happy to answer any other questions. Bye.
All right. So our next speaker is John Beverley, and he's the co-director of the National Center for Ontological Research. He's affiliated with IAD as well. And take it away, John.
Can you hear me? Yeah. Delightful. Well, thank you for having me. I don't know how I'm going to follow that act, but I'm going to do my best. So, hi, John Beverley. I'm an assistant professor here at UB. I've been here a couple of years. I'm in the philosophy department, though, so you might be wondering why I'm here. I sometimes wonder that myself. So, up front, I just want to say a bit before we get into the secretive stuff about, what I'm doing in the philosophy department and how it links up with the work that's going on in IID here. So I think of philosophy as a sort of a foundational place from which sciences emerge. I think historically that has been the case. Like Newton used to argue in print with philosophers. He considered himself a philosopher. Wundt, of course, like father of psychology, did the same. Chomsky at the beginning, the dawn of the linguistics age, was like arguing with Hilary Putnam in print, in philosophy journals. It's kind of like rather common. When I say, like, this shouldn't be surprising though, when you're on the cusp of an emerging science, you have a bunch of questions you need to answer. You're not really sure how to approach answering them. They are of interest, but there haven't been agreed on methods for how to solve them. So Newton is a great example of this. He created equations we could look at and make predictions and retrodictions based on. And then when Descartes and the Cartesians came, well, not Descartes proper, but the Cartesians who were also thinking about things like gravity would come to him and say, yeah, I see that you're modeling trajectories, but what is gravity? He would say, I feign no hypothesis, right? He's cordoning off the sorts of interesting questions you might want to answer as he's creating a science. I mean, we can poke at many areas where we don't have agreed on methods, right? Does God exist? What's the nature of consciousness? All within the realm of philosophy currently. Fingers crossed, hopefully one day we'll have methods on how to solve these, but you see the idea, right? We haven't agreed on standards or consensus around how to address these things. Now, philosophy is the study of, or that field of study that focuses on identifying methods. It's where new sciences emerge, like applied ontology. So I work in applied ontology. I build ontologies. I'm going to talk about those in a second. But we are now in something of a crucible moment, I think, for the field. We are becoming a science. Barry Smith is one of the pioneers. He's a UB professor, one of the pioneers of the field. He's been working on it for decades. He is in the philosophy department. We are creating the tradecraft and programs of study around the field now. Ontology, though, I should probably tell you more about what that is, right? So far, it's just a label, right? So let me do that by focusing on something of the driving challenge motivating our field. Psychologists want to study the human mind. Newton wanted to study gravity and trajectories and stuff like that. What do? We want to solve information silo problems. These things keep me up at night. Information silos is just information repository, like a management system, databases, whatnot, things you see out in this grand wide world of big data that can't be integrated easily with one another using standard computing strategies. If you pay attention at all to data in the wild, you'll see there's a lot of it. It comes in rapidly. It's stored in different systems. You as researchers are probably storing it in your own systems with your own local lexicons, probably hoping, fingers crossed, somebody comes along and unifies it or connects it up with data sets of researchers across the globe. That's what we're trying to do. We're trying to do that work for you because these things are dangerous. Silos are dangerous. You guys old enough to remember 9/11? Some of you are. I am. I remember 9/11. Real breakdown in like federal agency oversight in the kind of issues that or the threats that could be coming from adversaries overseas. Turns out, like, I know you've probably heard of the NSA too, right? NSA, National Security Administration. So NSA had information at the time about Al-Qaeda. Now, NSA didn't share that information with anybody unless they asked them for it. So the FBI could have accessed the information. They didn't know to ask the NSA because they didn't know the NSA had that information, and it wasn't easily accessible. Now, of course, the Patriot Act, which I'm sure some of you have strong feelings about, came later to help overcome some of the political and policy reasons for these sorts of information silos. But the point here remains, these things are quite dangerous. They can lead to attacks and security issues. They're also quite expensive. NIST last year did a study on information silos and how much they cost like mid to large scale businesses and like actual US dollars to overcome. And it was on the order of millions. It's like 20 to 40 million for mid-sized companies annually is spent on addressing silo problems in-house. Imagine how much it is at Amazon. I mean, and you can see why. So if you don't have a computing strategy to like integrate information, I'll tell you how it's done. People go do it by hand. They go into the databases. You've probably done this. You probably made students do this. They go to the databases, they pull this Excel file and that Excel file, and they go, I wonder if this thing left in this column is the same as this thing over in this column. And then they figure it out, and they do that again and again and again. That's expensive. It costs a lot of manpower, person power to do. They're hard to avoid, unfortunately, these things, which is why we have a field, a whole discipline designed to solve this problem. They're hard to avoid because I think it's somewhat in our nature, at least it seems like it's in our nature to create these things. Like it's very easy to model data, like to answer questions that you as a researcher are interested in based on some conceptual understanding of it that you have in your head that you haven't really thought through. That's just how we operate. It's how we operate in our day-to-day lives. It's how we operate as researchers. They're just fundamental questions you're not interested in answering, but you have something of a model in your head and you model accordingly. You're not the only one. Most people do this. So, in fact, even though people are familiar with the problem of silos and the sort of ontological solutions that might be offered, sometimes under the name of knowledge graphs or knowledge representation, even though they're familiar with these things, they still make silos, just like this gentleman who, this is from a Medium article here, this lovely gentleman. I pick on him a lot. I'm sorry, I have to. He's not alone. He's saying, look, you can solve these problems, these information problems, or silo problems that John is talking about, just by writing some scripts. Write some Python, or there are various libraries you can use to stitch these things together. No, not quite. This sort of easy path to the thing that we do, connecting, integrating databases, is a great way to just create different silos because everybody stitches the data together in their own way. They're not doing it according to a standard. Yeah, more examples. Just coast on Medium if you're not buying it. Like this happens all the time. But this is just another way to use knowledge representation or even ontologies to do the same information silo generation that people for generations have been engaged in. It's a very hard thing to avoid. Probably see why. So, I'll tell you more now. I grew up in a small southern town, poor, and I worked at a Walmart distribution center before I started college. I didn't start college until I was in my mid-20s, but I worked in a distribution center throwing freight, sorting things, categorizing things. And I learned some lessons here that have kind of impacted the way I approach applied ontology or just approach categorization or approach information silos, generally speaking. And I think I can encapsulate some of the things I've learned that really echo through the field by pointing you to this lunchroom that I used to sit in with my friends. Because one day in this lunchroom, my first day actually, I came and I saw a group of people sitting at a table. People had been there for years, and they were looking at each other, eating their food, and then every so often somebody would say a number, like 2, and then they'd all laugh. I watched. A few minutes later, somebody would say 16. Everybody would laugh. Like, what is going on? I got somebody later. I was like, hey, what is going on? You guys are not, you're just chewing, and then somebody says a number, and everybody laughs. What's going on? He says, listen, we've been here for years, all of us, like 20 years, some of us, working, throwing freight. We've heard all the jokes. So we just assign numbers to them. Why waste time? We got to eat. We don't have much time. It's a Walmart. They don't give you much time on break. So we know what 2 means. We know what 16 means. So I say, okay, I want to fit in with these gentlemen. So I learn the mapping. And the next day, I sit down with them. I'm so proud, eating my sandwich. I wait for the opportune moment. And I say 5. Nobody laughs. Nothing. I'm so confused. I go talk to my friend and I say, hey, what happened? That was the right joke to tell at the right time. And he's like, that's how you tell it. It's important. That's how you tell it. There's some truth in that. So our field, what we're trying to do is integrate heterogeneous data sets at scale to support interpersonal understanding, like communication across people. And then also apply this in the real world, like for various missions, to improve data quality and governance. And really, like, if If you're thinking of it in terms of programming or something like that, to provide like an explainable foundation for code. It's one of the other things I like about what we do. And we work, when I say at scale, I mean like federal government level scale, like Amazon level scale. Like we want to create interoperable, or we want to interoperate data sets across organizations of that level. But it's important that we have to focus on how you do it, how you tell the story, how we approach it. Anybody can go build an ontology. Anybody can go build a knowledge graph. Anybody, just like anybody can build a data model. Anybody can go build an Excel file. But it's how you do it that's the important thing. And what we do at UB, what we do in the Applied Ontology program is focus on the tradecraft. How do you do it? How do you do it so it's scalable? How do you do it so it's, we don't want to say future-proof, but more future-proof than it would have been otherwise. So we focus on the how. And here, the underlying conceit here is that we're trying to model, as philosophers, as logicians, but also as engineers, some fundamental structure of the world. Any two speakers of a given natural language share some underlying formal structure. It may be hard to suss out. That's fine. That's what we do. It's hard to do it. It's hard to automate it. That's why I'm not worried about LLMs yet. But honestly, if they could pull it off, I'd be happy with that because my job would be a lot easier. But until then, we have to think about these things. We have to be very careful about what speakers mean cross-person. This is the human-human side. So when I talk about integrating, interoperating at scale, there are three axes to keep in mind. One is interoperable between humans. What's going into the database? How do you get consensus around what's going in? There's also, how do you connect that when you've recorded it from one machine to another? That's that information silo-y problem. And there are various strategies to do this, transformations of data and whatnot. And if you've got some clean data put in from human to human interactions, it makes this easier. But ultimately, the conceit here is that any two heterogeneous databases will share some underlying structure. And what we do is we try to make explicit whatever implicit structure that is. There's also, of course, the inputting from the humans who have agreed into the machine, so the human-machine axis. And this is interoperability between us and those things to build trust, like make it easy to do. We aim to build machines that reflect the underlying formal structures that we live, in which we live, because we want to provide trust. I want a sophisticated robot that I can trust the way I do a calculator. Although I'm saying this is probably among a bunch of engineers, and I remember when I was taking engineering classes, I would both do the math in my head and with a calculator, because who knows, right? Like sometimes they're wrong, even though they are. But the idea, though, we're trying to create common logical structure across these different axes, but from human to machine, to machine to machine. And the conceit in our field is there is such a common structure. We just have to sort it out. And we're pretty successful with this. So Barry Smith, pioneer of the field, kind of pioneered this methodology. Prior to this, still today, people will try to go and they'll model the world. They'll like, according to how they conceive it to be. They'll model their concepts about it. Or they'll model whatever they need to model on the ground to get their project off the ground, like to make progress. Whatever the data looks like, that's what they'll build a model of, right? Of course, when you're thinking about modeling concepts or you're thinking about modeling just the data, that's not really extendable to new use cases. It's not really thinking about interoperating that stuff with other data. I'll give you an example, one that was hopefully compelling, or at least, but it's a recent example, one that you should be frustrated by. I certainly was. I was helping some groups model data about drones tracking fentanyl across the border. And I was in a group with a lot of the subject matter experts who actually look at the data in real time. I was also there with a bunch of the IT people, with the data modelers, and we were talking about like pattern identification, because they couldn't really, the problem they were trying to solve is we can see sometimes like drone patterns, like when they come over, like we can kind of tell that this is a drone or that's a drone. Well, we can't like get our get anybody there to intercept it fast enough. And so what they need to do is not like identify patterns when a drone is flying and dropping off fentanyl. They typically fly straight, by the way, whereas lots of other people will meander. What they do need to do is like make predictions almost at liftoff that this is going to be a problematic drone we need to intercept. They need to do something like that. Now, they were thinking, just as I said, they were like straight paths. That's what we need to focus on. That's how drones fly when they're dropping off fentanyl. That makes sense, right? You want to get in, get out. Drones are expensive. So I asked at some point, I said, hey, okay, you've got these patterns identified. Like you can see the trajectories, you can see geospatial location and all that good stuff and time and whatnot. What about the weather? Okay, the drone carrying some narcotics, heavier than normal. It's really windy, especially over Lake Erie. Don't you think the wind will like impact the trajectory? And they were like, yeah, that's great. One, I was upset because they thought they were surprised. They were like, that's a good insight. And I'm like, no, it's not. It's not a good insight. You should have already thought about that. That was one. Two, they couldn't integrate the data they were collecting, the geospatial data they had, with weather data. They actually had a database full of weather reports, like vetted weather data. But the only way they could stitch them together was literally a guy sitting there copying from one Excel file to another. Actually, it was worse than that. I won't go through the details, but that's the state of the game. This is not uncommon. It should frustrate you, but it's very common. There wasn't a common semantics that they had laid down on top of these data sets so that you could just push a button and make the connections. Now, they have that now. You're welcome. And they have that now because we used basic formal ontology, which advocates, is underpinned by this kind of common logical structure implicit in the data. This picture allows us to lay that semantic layer over the top of these data sets. They can just push a button. And there's still problems, but you know. I won't go through here, but just so you know, we're quite popular. It's an ISO standard basic formal ontology. I won't go through the details for this talk, but it was the first ISO standard top-level ontology. And it's also mandated for use across the DoD and the IC. So they all have to use it. That's one of the reasons my inbox is so full all the time. They need help. Okay, but this was a talk aimed at secrets, right? That was the tagline. So I tried to run through some of this, but let me talk about secrets now as an illustration of the tradecraft, right? So I want to talk now then about what is a secret. And remember, I'm trying to unpack, and you'll see me unpack here, the implicit logical structure, hopefully, of secrets. Aiming through natural language, through various use cases, and ultimately I'll be trying to identify, and maybe you can help me with this because it's tricky. I can identify like hallmarks of secrets. So we know they're everywhere. Secrets are everywhere, right? Like we're familiar with this. Here's a study from not too long ago. The average person keeps 13 secrets, seems like, at least. 5 of which they've never shared. It's interesting. Now, here's some like categorization, rough categorization of the types, just so we have something to keep in mind. You'll see things like, there's a lot of like sexual behavior here. There's some finance stuff, hobbies, trauma, things of this nature. It's quite the gamut. Friends keep secrets. You keep secrets from your friends, no doubt, sometimes to protect your friendship, like our old guy here in Gandalf, right? Sometimes you want to keep secrets from friends. That's okay. It's kind of normal part of communication or relationships. Maybe you uncover or reveal secrets as you get more intimate with somebody. But nevertheless, there are at some point some secrets between you. Newton, he's back. He had some secrets. I know, he really liked to think about turning lead to gold, among many other things. He was 200 years after his death, it was discovered that he spent a significant portion of his life trying as an alchemist. So maybe he's trying to make alchemy a science. I don't know. He had a good track record. If I was as successful as him, I would have tried it too. But nevertheless, this was a secret from many people. He's also associated with various secret societies. So these are societies, groups that have some kind of like privileged knowledge, secret information. Like these Hermes Thrice Great or Thrice Great. This is a very large group of like, I like to call groups that like claim to have knowledge, like secret knowledge of the world, like not like Freemason stuff, but more like we know stuff. Like I like to call them the Illuminati. So this would be the classification of an Illuminati group. Secret knowledge, but like secret societies that come up all out throughout history. There are trade secrets, right? My favorite, of course, being 11 herbs and spices. But also the formula for Coke, or at least French Coke or Coca-Cola. You can ask questions like cocaine and caffeine, but how much? You have the list. You don't know how much goes into what. There are also military secrets, secrets that can keep you safe, not just from your friends and your relationship there, but from adversaries. If you talk too much, you might die. Like, so serious. Of course, there's an entire classification system, or at least there used to be, i.e. political commentary, but I'm going to move on. There, security clearance, there's all sorts of information out there that we're not allowed to reveal to the public because of the damage it might do. Secrets. Not everything is a secret, even though I've given you a lot of examples of secrets, even though sometimes things are called secrets when they're not. So they're sometimes described as historical secrets. This is sort of information that we're just never going to uncover, right? Sometimes it's called a secret. I think this is a metaphoric use. But like the Sea Peoples, like they attacked Egypt, they kind of swept through the they swept through and created societal collapses back in the 12th century BCE. Nobody really knows anything about them other than like descriptions here and there. Sometimes this kind of invasion is called a historical secret. Again, I think this is metaphorical. Not everything's a secret, even though it sounds sexy. If you call this a secret, I don't think it's quite the same as what we were describing. There are also open secrets. Remember I was mentioning the NSA earlier? For a while, this was supposed to be classified. The joke in this house was that it was NSA meant no such agency. It was a secret. Of course, now we know it's an open secret. It's not actually a secret. Again, I think this is just a way of speaking. We don't actually mean this is a secret in the same sense as something I keep from a loved one that I think if I were to reveal would damage our relationship. It's used in many ways in natural language. Now, we're not interested so much in what we do in linguistics, although linguistics is a good default. I like to think about it this way, like natural language is a great starting point for intuitions about how to model the world, but it's not the arbiter. If my models, my ontology, my logic differs from natural language, I owe an explanation. But if it aligns with it, I don't really owe an explanation. That's what I mean by default starting point. But ultimately, I'm not interested in just doing linguistics. I'm interested in doing something deeper, the nature of what is referred to by secret. And here's some questions we might ask ourselves based on the examples I was just working through when we're investigating. I think it's plausible that secrets are some type of information. And when I say information here, you don't have to get hung up on it. I just mean something like copyable patterns that are about things in the world. Secrets seem like a type of that, some kind of copyable pattern that's about something, putatively about something in the world. We might ask how they're created, how they persist, and how they're destroyed, too, kind of boundary conditions and then persistence conditions. Again, the structure of the secrets. I say information. They're just about something. Check it out. A standard example of information that's about something is called a proposition, at least in philosophers speak. They're like the content of assertions. When I say it's raining outside, I mean like outside, there's like rain pouring down, right? The content is raining outside. And how would you check it? You go, look, it's about that, right? Now you could say the exact same thing in English or another language and you'd have the same meaning. The thing we share in common, that's the information, and it's about that. You might think information or secrets have the same sort of structure too. Now, propositions are always true or false. It's kind of characteristic of them. So when somebody says snow is white and somebody says Schnee is weiß, and they have this same pattern in common, that is the meaning in common, it's true or false. It either is or it isn't. Make sense? We might ask a similar question about secrets. We might say, are secrets propositional in that sense? If you have a secret, is it always something that's true or false? Now, of course, I'm getting ahead of you here because I don't think that's true. This is the sort of question you might investigate. What sort of structure does this type of information have? Is it a sort of thing that's always true or false? A friend of mine, Agent Menson, he's part of, he's tasked with keeping a specific document as well as the document as a whole a secret, and then the document it contains directives such as attack at 1300 hours. Now, attack at 1300 hours is not true or false. It's an imperative. It would be incorrect to say it's true or false. It's a command. You do it. There are different kinds of conditions around things like that. You might also think of somebody tasked with keeping a secret of a clan, namely the know-how to produce rich tapestries of forbidden events or something like that. I don't know, they wouldn't tell me all the details, but the idea being knowledge how, like know how. You might not exactly be able to articulate clearly in natural language, in a propositional form, the steps you might go through to convey expert knowledge to somebody. There's some kind of know-how. You know how to do it, even if you don't know how to describe it. Like riding a bike. It's a simple example. You might walk through all the steps you might take to ride a bike. How about riding a bike BMX expertly style? Can you walk through those steps? It's not even clear to me that you could. If so, you might nevertheless keep something like this secret in your head. It's not propositional. You couldn't even articulate it as something that might be true or false. So, upshot, I don't think we should consider secrets as restricted in that way. They're not just true or false, although many secrets are putatively true or false. We won't limit ourselves there. Perhaps more interesting is we might think of how they're created. I think one creates this sort of information when they choose to conceal it from somebody they might believe want to know. Look, I'm not going to tell you how long my toenails are. It's not a secret, though. You just don't care, I assume. And that's why it's not a secret. I don't even think you would care. Right? There's all sorts of information like this. I'm not going to tell you, but also I'm not concealing it from you. Why would I? You're not going to be interested if I were. In addition, it seems like secret keepers, the person who's holding a secret doesn't have to believe the information would like benefit somebody, right? Like withholding a gambling addiction or knowledge about a gambling addiction, or they might not actually, they don't even have to believe that somebody would want to know the information at all. An infidelity, you might keep that secret, right? Like it might not be valuable to convey to them. It might be very disruptive in your entire relationship. It might just ruin the whole thing. Now, of course, in some sense, in some real sense, your partner probably wants to know if you're cheating on them. In that way, it's a secret. Persisting, though. All right, here's some examples. Those are some examples about how they're created, right? You can see them. Somebody has to want to know to some extent what you're concealing from them. Not just everything's a secret. If a secret's intended to be kept from many more than one individual, which is possible, you can keep a secret from a group. Membership in the ignorant group can fluctuate. I can keep a secret from all of you, but then as you leave, somebody could tell you the secret. Somebody else could populate in and come in here, and we can keep the secret from them as well. The secret persists. Somebody in the group could learn it, this information. It could be revealed to them. But as long as there are people who don't know anything about the secret, at least one person, it's still a secret. At least one member of the ignorant group has to remain. Secret keepers must believe the information has not been disclosed to people. I'm not keeping a secret from you if I also believe you know it. It's not a secret. I think you already know it. What am I concealing? Now, I could be concealing the fact that I know that you know. That's a different secret. Secret keepers intend the information not to be revealed. I'll skip through some of this because I'm nearly at time, but I do want to say, I want to get to something that's a little, I find fascinating. This gets to a wrinkle in what I've just suggested that you might ponder over. Secrets can be destroyed if a secret keeper doesn't actively block a believed revelation, or if all ignorant parties no longer exist. But no secret remains so forever. If there are no individuals believed to care about the secret anymore, it can't be a secret. That's what I said, right? You have to think you care. You have to believe you might care to know. But that means all it takes is for somebody in some cases to just not care that you're holding a secret from them. And now it's not a secret. That might seem a little weird. This is from a Marvel comic book. This is Thanos. He's beating up this guy named Black Bolt. Thanos, the big purple dude, is trying to find out where his son is. Black Bolt, the guy he's holding, knows where his son is. He won't tell him. Thanos beats him up a lot. And Black Bolt's like, he doesn't say anything. I'm not going to tell you anything. And at some point, Thanos says, fine, keep your secret. And he goes and finds another way. He's like, whatever, I don't have to listen to you anymore. It seems like Black Bolt had a secret. And then suddenly Thanos is like, whatever, I'll do something else anyway. Get out of my face. And now it's not a secret anymore. That should seem a little weird. And if you have any thoughts about how to solve that, let me know, because we're trying to uncover the hallmarks and the structure of secrets. To summarize, though, secrets are a species of information. They don't have to be truth apps. Information becomes a secret when an agent intentionally conceals it from another they believe might want to know. And for it to persist, it must be kept from at least one individual, otherwise it's no longer a secret. And if a keeper recognizes a potential revelation, they must act to prevent it. Now, I didn't really talk about that one. That was the part I skipped over, but the upshot basically is, if I think you're about to learn a secret, it's about to be revealed to you, and I can stop that from happening, and I don't do anything, I've just given up the secret. All right, there you go.
Any questions?
Questions? Any solutions to that wrinkle? You want some of that?
So in terms of, these philosophical things are, this was out of the blue, so I didn't really expect this talk. So from what perspective are we looking at this? Is that this study of secrets is sort of motivated by potentially some application that sort of makes it worthwhile for us to sort of spend time thinking about it, right?
Absolutely.
So
there are a lot. So there are a lot of applications. So the reason I don't start with that is because of the nature of the work, because it's a secret. But there are a lot of applications of this. There are a lot of working groups I'm part of, for example, with the feds, where we're talking about types of information and degrees at which it's classified, degrees at which it's not, aspects of it being classified and aspects of it not. So I give you an example of the sort of puzzles we sometimes encounter that have really motivated a lot of this work. If you're building ontologies and you're creating connecting data from one group to another, and you're creating making explicit that implicit logic underpinning them. We use this to run reasoning machines over, inference engines over, so we can uncover new facts, cross-data facts. For example, novel patterns that drones might take when wind is impacting them. This might be new information. So there's sort of this issue that comes on when you're working in certain spaces. If you have open source data here, you have open source data here, you put them together and infer information. Sometimes that information can be secret or classified all of a sudden. For example, when a standard situation is, if you take open source information about a website and you combine it with open source information about this type of website framework, hacker tools, etc., and you combine that all and run inferences over it, you might identify vulnerabilities or exploits in the website. Now, if that is a government website, And for many contractors, that immediately becomes classified information. Not for all. The upshot being there, if you're a certain type of contractor and you identify an exploit or a vulnerability on a government website, it is immediately classified for you. Now, identifying how that works, where that works, data about contractors and non-contractors who encounter that information is a big problem. We have different data sources modeling it, but not everybody agrees on what a secret is. And secrets ultimately will be the foundation on which classification is grounded.
That was good. So yeah, something to think about.
Yeah,
it is fascinating. Thanks again. Hope that was it was two very different kinds of talks. One where, again, like something that we all experience. So we use a lot of applications to sort of find information about a place and whatnot. And now how can you do that with things that are ubiquitous? You have Wi-Fi signals. Can you sort of use that to map spaces and find yourself somewhere without needing to do something very complicated, right? So, those are the kinds of things that technology can solve, and new ideas that make that easier. Now here there is this whole philosophical thoughts that, I mean, obviously are sort of you're thinking about those things to solve real issues, right?
Yeah.
Like, so to see how to find solutions for that, where you accidentally discover secrets.
That's right.
Then sort of you have to figure out how to tighten everything or whatever, like what the consequences are based on that. So two nice talks, and thanks
Thank
again,
you.
John.
Yeah, I'll say real quick. So if this is too heady for you, too philosophical, don't worry. So I teach a lot of courses that are closer to the engineering side. So we work with a lot of folks that you're in disciplines you're probably more familiar with than this. I train specialists to do the ontology work of the sort that I just described, but they have to learn how to talk to engineers, because we could build these models, but we're not going to use them. This is not like code. It doesn't execute. It's a model. Now the code executes. You go build the code. So we have to talk to folks who actually use these things. So if you want to hear more about that, I have a whole YouTube channel, like Bridging the Connection here. And I teach a lot of classes that I put on GitHub because I want everybody to know what we're doing. So, or you can just email me.
Thanks, John. And so there's some snacks and water, and hopefully you'll come back for our remaining talks during the semester. Thanks.